Okay, so we're going to start a new topic today. So Green's theorem is the name of the section here. But we're going to start off with some ideas that are actually going to apply to a bunch of what we're going to do in the rest of chapters 6 and 7. Turns out these various theorems that we're going to cover over those two chapters actually have a lot in common with each other. And what they have in common is very hard to formally make precise. So what I'm going to do is I'm going to instead develop them, develop intuition that arrives at them as reasonable, seems like they ought to be true, right? I'm not going to call these proofs, right? But I want to kind of motivate them by analogous means. And so here are some of the tools that we'll be using for that purpose. So we'll start off with the idea of what is a quantity. This is not a big deal. The idea of a quantity is it's something that you can define on an area. Call this a quantity on areas. And so, for example, if you give me an area, like R here, we can talk about the amount of mass in that R. I'm going to call that a quantity on the region. And, it's not a deep point, right? I can talk about the area of the region. I can talk about the perimeter of the region. Any rule that when I give you a region that you can come back and tell me what the value of that quantity is. So sometimes they're physical, sometimes they're geometric, sometimes they're neither. Okay. All right. Now, the kind of quantity we've talked about in the past, I've actually done quite a bit of stuff with this idea of an accumulating quantity. And I just want to be a little bit more explicit about what I mean by an accumulating quantity, specifically a quantity that accumulates over areas. Now, what we mean there is that if you take an area, if you cut it into pieces, and look at the quantity in question on the individual pieces, that it adds up the way that you would kind of expect that it would. And the way I've been saying that, and in general the way I like to say this, the whole is the sum of the parts. Right? So mass has this property. Right? If you were to look at the whole region and ask what's the mass of that whole region, well, I don't think it's going to surprise anyone when I say that would give you the mass on the left region plus the mass on the right region. Well, of course, right, it's stuff. How could it be anything other than that, right? I hope that's intuitively satisfying. Okay, so mass is an accumulating quantity. Likewise, area is an accumulating quantity. Hopefully not surprising. Now, just so you won't take this property for granted, let me point out one that is not, and that is perimeter is not an accumulating quantity. And I think a reasonable pitch. If I were to ask what's the perimeter of this whole region, it doesn't have anything to do with this little dividing line. But if you were to look at the perimeters of the individual pieces, the perimeter of R1 does include the length of that little dividing line, and the perimeter of R2 does include the length of that little dividing line. The whole here is less than the sum of the parts. Does everybody see that? All right. So this property, we're going to use it a lot, this accumulation over areas. We use it a lot because in some sense that's kind of what integrals are about, is quantities that have this property. But just so we don't think that this is some magic wand that applies to everything that you'd ever want to compute ever in your any situation, let's recognize not everything does it. Okay. All right. Now the next observation is a little weird. I'm going to propose that we can think about accumulating quantities in a certain way. It won't be clear immediately why I would ever want to do this. But don't worry for the moment about why I would want to do the following. Let's just focus on whether it is okay to do the following. And here's the punchline. If you have an accumulating quantity, you can view it as being distributed over the area. And to be a little bit more blunt about it, it behaves like stuff. Right? So mass is a kind of a stuff. right? It's physical, concrete. Stuff is a really good word for this, what I'm talking about here. So not every accumulating quantity is stuff, but you can treat it like stuff. So now let's think about, what could go wrong here if I were to take something like a nice example, I think, is work. Let's, before I go with my hypothetical, let's imagine on this region here, maybe this is the bottom of a swimming pool, and there's, something growing on the bottom of the pool, right? Somebody didn't put the chlorine in there, and there's stuff growing all over the bottom of the pool, and I'm going to have to get down there with a toothbrush, right? And scrub. And maybe, for whatever reason, there's more stuff growing on the left side of the pool, maybe in the deep end, and there's less stuff growing in the shallow end. I don't know, I'm making this up, right? But it's going to take me a long time with a toothbrush to scrub all of that stuff off of there. Okay, well, the amount of work it'll take me to scrub off in one little region, the amount of work it'll take me to scrub off in some other little region, right? I don't think of work, the number of calories I'm going to burn in doing that. I don't think of that as being physically located in that little region. But I could think of it that way. And if I did, the upshot, would be, well, I mean, if I were to think of it as being in the region, I would effectively be sort of imposing that quantity would have the feature that the whole was the sum of the parts. But it is. It's an accumulating quantity. So, weird to say it this way, but if I want to think of work as being a physical stuff that is physically located in little regions distributed over the entire area, I can do it. It's okay. It won't create any problems. Now, again, why I would want to do that, we'll get around to that in a couple minutes. All right. Now, here's the thing. Again, accumulating quantity. We can think of it as physical stuff. What else do we do with physical stuff? And here's an example. We talk about the density of that stuff, right? So mass is the easy example. Mass density means just basically mass per unit area. Now there's the little sticking point, the little formal little detail that if the density is not constant, how do you talk about density at a point when in fact at a single geometric point there is no mass? Mass is spread out over areas, right? So the idea is you look at little small pieces of area. You look at the mass in a little small piece of area. You divide by the area of that small piece of area, and then as you take a limit, as that little area gets smaller and smaller and smaller, you're effectively computing density effectively at a single point. So that little detail with the limit, etc., is necessary inconvenience, but really not that much to worry about. The point of a density is that it is what you can multiply by size to get stuff, as we've done several times in the past. Okay, so again, you can do this with any kind of stuff. Reminder, accumulating quantities, we can pretend that they are physical stuff. And so I'm going to do the same thing here, not just for mass density, like so, not just for population density, different kind of stuff, but still stuff per unit area. But we're going to do it for these non-stuff accumulating quantities like work. I mean, again, how many calories am I going to burn from the exercise that I get from rubbing on the bottom of the swimming pool with a toothbrush, right? Well, I can talk about work per unit area. Whether it is or isn't actually physical, irrelevant, right? It behaves as if it's physical, and I think it's actually pretty intuitive in this case, right? I mean, per unit area, each little piece of area I've got to rub with a toothbrush, and the bigger the area, the more I'm going to have to rub off for that entire area. So effort per unit area, pretty natural, I think. Everybody buying it? and I claim we can do this for any accumulating quantity. And by the way, there's an obvious natural next step. If you have a density, then you can compute it with an integral. So, for example, the easy first example, mass, has this property of accumulation. And I'll remind you that the way I like to pronounce this equation is mass is the sum of a bunch of little pieces of mass. This is just saying that the whole is the sum of the parts, right? So you get this because it's an accumulating quantity, and then you get this because that's what densities do. Densities are what you multiply by areas to get stuff. Right? So punchline, we have effectively a theorem that because mass is an accumulating quantity, we can compute it with an integral of a density. Again, now old news, we've done that a million times, but now we can do the same thing for any accumulating quantity. That's a broad statement, right? Any accumulating quantity. For example, work. You want to compute the amount of work it takes to do some task? It's an integral of work density. Whatever that means. Everybody on board? So let me broad stroke now tell you why we're doing this. We are doing this because it's going to turn out that there are some extremely important accumulating quantities that we're going to be studying a lot in the rest of chapters 6 and 7. And because they are accumulating quantities, we're going to be able to go through this whole process just like we did here. They have this property of accumulation. I'm going to think of them as stuff. I'm going to talk about their associated density, and I'm going to add it all up with an integral. Just for an accumulating quantity that I have not yet identified. Okay. All right, now for whatever it's worth, everything that we did here we talked about on areas. So in some sense, everything we were doing here was about two-dimensional quantities. So mass distributed across areas, or the amount of work that it takes to clean an area, stuff like that. But you could just as well talk about stuff that accumulates over volumes. And you get an associated notion of density as quantity per unit volume, whatever that quantity is. Right? Again, as long as it's an accumulating quantity. And then likewise, there are single variable versions of this. And again, whatever that quantity is, we're going to compute it as an integral of that quantity per unit length in the single variable case. Okay. All right, so that's all broad stroke stuff. Now I'm about to develop our very first new accumulating quantity. It does take a little bit of setup, so you're going to have to bear with me for just a second here. Before I can define the accumulating quantity, I have to tell you what boundary means. Now I think y'all pretty much know what a boundary is, right? So for example, if I have some region like this, you're probably already accustomed to the idea of thinking that the boundary, well, it's this curve that's kind of the edge, right? It's the border between where the set is and where the set isn't, right? And boundary, in that sense, I hope is a familiar idea. Here's the new notion of boundary. Boundary now, henceforth, is an oriented thing. This being a curve, this boundary I need to understand as an oriented curve. It's not good enough to just be a curve. We're going to need it to be an oriented curve. So there is a rule. Oh, before I forget, let me talk about notation just a little bit. You'll notice right here that I'm using a partial derivative symbol as a kind of a placeholder for the word boundary. This is a pretty common notation, very common actually. So there's a reasonably decent explanation for why we would want to use the partial derivative symbol to represent the word boundary. It's not worth our time to go into here. If you're curious, come talk to me. I'll be happy to describe it. Anyway, this is a standard convention, so heads up when you see the partial derivative symbol next to a set, that means boundary of that set. All right, so here's the convention, standard convention for how we talk about boundaries and specifically how they're oriented. If you have some region like this, and we've got a little piece of its boundary curve, let's see here, we'll do it like this. This piece of the boundary curve, like so, right? Here's the rule. The orientation, the correct orientation for this piece of boundary curve is whichever direction you would go, in this case, as I have indicated there, such that as you walk, right, this is me, my little feet here, I'm walking along. As you walk in that correct direction, the set's on your left. That's the rule. Right? So the region whose boundary you're talking about needs to be on your left. This is a completely arbitrary choice, but this choice got made a long time ago, and it's been the standard accepted norm convention for how we talk about boundary orientations ever since. And so it is, to be fair, yes, it's arbitrary, but it is a standard, and so it is not optional. Right? So always, whichever way puts the region on your left. So now you can kind of see what I've drawn here, that here I've only, the region is in light green up here. There's a much larger region, and we're just looking at sort of part of it. So in this case, we're moving sort of what you might call to the right. But notice if we were looking at maybe sort of the top part of the region, if I were to look at, the sort of the top part of the boundary, which way would I have to go across the boundary? Here's the boundary curve. Which way would I have to go to put the region on my left? And again, you got to imagine, right, walking along, region on the left, I got to go that way. Which is to the left this time instead of to the right that time, right? So it's a little bit different. But in both cases, the region is on my left. Yes?
So can you just choose which direction you're moving in?
You have to choose so that this condition is satisfied. Does that make sense?
Yeah.
So there's always two choices, right? Whenever there's a curve, there's two different directions one could go. One of them will put the region on your left, the other one will not. And you have to choose the one that does. I saw a hand somewhere. Yeah.
Is there like a right-hand rule way to figure it out?
Yeah.
Like if it's coming out of the page.
I'm not gonna bring that. I think it's gonna create more confusion than it's gonna resolve. So, so short answer, yes, but I don't think it's a good way to think about it. Yeah. But feel free to talk to me about that later if you'd like. If you want to compare, yeah.
Yeah, could you please repeat again why the arrow is upside down?
Why the what now?
Why the orientation is to what, like?
Yeah. So as you walk this way, is the green again? So this is me, right? I'm going like that. I'm pointed that way. The region's on my left.
Okay.
So that's the rule. Walk whichever way puts the region on your left. Okay. Yeah. Right. Okay. Now there is a kind of a compact shortcut streamlining of this that is right most of the time, but not always. Okay, so I present this as a secondary, as a shortcut, but please do not hang your hat on this because it does not always work. This will give you wrong answers sometimes, and I'll point out in a moment what the wrong answers are. Notice that if your region is what we call simply connected, in other words, it doesn't have any holes in it, as I've drawn here, notice that wherever I might happen to be on the boundary, the way that I go to put the region on my left is always counterclockwise, right? The whole way around. It's always counterclockwise. If I were to walk around that, little green little park there, as indicated, the park would always be on my left. And so there is a temptation to say, the convention is that boundaries are always counterclockwise. But they're not always counterclockwise. That's a coincidence based on the fact that we're going around what you might call the outside part of the boundary. If you look over here now at this other example, and let's think about, what would I do if I were, let's say, at that point? Well, that direction, which is counterclockwise. If I were at a point like this, I'd be going that direction, which is counterclockwise, region on my left. Seems like counterclockwise is still working, but if I were to look at a point like that, this is a point on the boundary of my gray region here, right? And which way do I go to put the region on my left? I would have to go this way, which, I'm sorry, but if you were to keep going that way, you'd have to describe that as clockwise, not counterclockwise, right? So this rule does not always work. It only works if you're going around the outside part of the boundary. Now, good news, very often you are. Possibly even usually you are, right? But anyway, just be aware, counterexample. Okie dokie. So, here we are. We're ready to do it now. I'm going to tell you what the brand new, very important accumulating quantity is. It does presume that we're interested in a particular vector field F. And with that given, here's the new accumulating quantity, boundary circulation. And it's very surprising. It's very non-obvious that this has this feature that I claim. I claim that this is an accumulating quantity. It doesn't feel like it ought to be, but it is. All right, so let me try to persuade you that this is an accumulating quantity. Oh, sorry. Let's look at this. I've got this lump here made up of two pieces, D1 and D2. Let's look at the left piece here. This piece of area called D1. And now let's think about how would I represent on this picture the boundary circulation for D1. Well, okay, so I'm going to have to take this region D1. I'm going to have to look at its boundary, and then I'm going to have to compute a vector line integral representing the circulation around that boundary. And so I would be doing a line integral like so, because this is what you might call the first part of the boundary. Notice I go in the direction that puts the region on my left, and then I continue around the boundary like so, again in such a way that as I go, right, as I continue to walk like this, the region is on my left. Okay, so boundary circulation on D1 is a line integral over this purple curve. Everybody with me? Okay. All right, let's see here. So let me circle that here. So there's the boundary circulation for D1. Let's do the same thing for D2. Here's D2. Again, sort of two-dimensional region there. And, oh gosh, I feel the compulsion to color that in all the way. So now let's think about the boundary circulation on that. Now, how would I compute boundary circulation on D2? I've got to think about the boundary, literally, of D2. The boundary of D2, I go across that same edge, but this time downward, because that's the direction you go that puts the region in question, D2, on your left. Right, again, we're thinking right now about the boundary circulation on D2. So downward to put the region D2 on my left, and then continuing sort of like that, again, so that the region is on my left. Everybody's good? Okay. So that's the boundary circulation for D2. Now let's ask, did we win? Does this work? It is what I've represented here as the sum of the individual boundary circulations. Does that add up to the boundary circulation of the hole. It's not looking good right this second. In particular, notice that I've got all this stuff in the middle here that kind of seems wrong, right? This line integral, I'm going across this cut edge between D1 and D2. I've got line integral across that edge. That's not part of the boundary of the hole. It's not part of the boundary circulation of the hole. So it looks like we've got a problem. But here's the thing. We actually have two problems. I'm going across this cut edge upward as part of the boundary of D1, but I'm going across the exact same edge downward as part of the boundary of D2. Same edge, opposite orientations. That means that when I compute those line integrals, I'm going to get the exact same value but with opposite signs, and they cancel. How we doing? Does that make sense to everybody? So let me just represent that super convenient fact. Because they cancel, I can just get rid of that and check it out then. What I have left, in other words, having gotten rid of the confusing little zero that was in the middle, the sum of the parts is the boundary circulation of the hole. So the hole is the sum of the parts, unexpectedly. Everybody good? Okay. Now, just so you aren't thinking, well, that's a lucky coincidence because you only made the one cut. Let's entertain here what would happen if you cut something into a whole bunch of pieces. And here, again, I've only drawn part of a region, and you can see part of the sort of the boundary there. And what if I were to cut it in, all these? Oh, whoops! I'm getting the pencil. Pencil mode here. And what if I were to cut along all of these, lines like this and like that? Right, and we could do all those cuts. And then now let's think about the boundary circulation, for example, on this piece. Well, it would be along these four edges like that. And then let's look at the boundary circulation on this piece, and it would be on these four edges like this. Oh, 5 edges. There's that little one right there. Like that. Right? And do I get cancellation on all of the shared edges? 100%. Totally. Because look, every shared edge, if you think about it, every shared edge, like that one right there, that shared edge oriented upward is part of the boundary of the left side, oriented downward is part of the boundary of the right side. Opposite orientations on the same edge, they cancel, poof, gone. And likewise for every other shared edge. Appears twice, opposite orientations, cancels. Appears twice, opposite orientation, cancels. Etc., etc., etc. On all these shared edges, all of that just goes away. And you're left then just with... Oh, whoops, I didn't. I wanted a different color. Sorry. You're left with just the boundary of the hole. So, boundary circulation is an accumulating quantity. Super surprising. Now let's see here. Let me do that. Boundary circulation accumulates. Yeah. Yes.
Do you have a situation where they don't cancel?
Nope.
No. Okay.
This is an always thing. If you have, okay. I mean, look, I don't want to get into the weeds of really weird, anomalous, sticky situations. We're thinking about nice, regular regions and stuff like that, and the cancellation always. Yeah.
Okay,
right.
thank you.
Yeah. Okay. Okay. Now, why were we interested in this in the first place? Let me remind you, going way back here, if you have an accumulating quantity, you can treat it like it's physical stuff, weird though that may seem to be. If you can treat it like physical stuff, you can talk about its density. Once you talk about its density, you can add it up with an integral, and you get yourself an integral theorem. And again, This works for any accumulating quantity. Well, we've just found ourselves a new accumulating quantity. And so boundary circulation, we can make this argument. And that's what we have here. Boundary circulation, it behaves like a physical stuff. We can treat it, therefore, as stuff and talk about its density. And we're going to add it up with an integral. Now, there's some notation to be discussed here, and I'm going to come back to the notation in a minute, but here's the sort of broad stroke of that argument. Again, we've talked about this stuff, this quantity called boundary circulation, and by the way, side note, we're going to get real tired of saying the word boundary over and over and over and over and over again, so in fact, most of the time people just say circulation. Right? And in a context like this, it's understood that it means boundary circulation, and in fact, notice it even says so right there. Boundary circulation, right? So, streamlining it, circulation. Represented, by the way, again, by sigma, just like we did last time. We've got this quantity. We've observed that it is an accumulating quantity, so the whole is the sum of the parts. And because it's something I can treat like a stuff is density times size. And this right here, curl, that's the density in question. And you'll notice that's the very first, that's one of the first representations I have here, is I'm calling this circulation density. And curl is this common notation for that circulation density. What do you think? That cool so far? All right. Good news. We can compute curl. Oh, I should leave that circled. We can compute curl, aka circulation density. Here's the formula. It turns out to be showing that that's the correct formula is not that bad. The book, I believe, if I remember correctly, has a calculation in there where they show how you can derive this formula. I'm going to say it's details. Now, it's very important details, sure, but from a conceptual point of view, from a how do you make the pieces fit together in your head and gain satisfaction and good intuition for what Green's theorem means and how to think about it, I don't think those are important details for our purposes, so I'm not going to use class time for that, but if you want to see it, it's in the book, feel free. So we have a formula. That's what two-dimensional curl is. We have an interpretation. It's circulation density, and we'll talk more about that in just a second. For whatever it's worth, the result that we have here that says that this circulation integral can be computed with a double integral over the interior of the curl operator. This is known as Green's theorem. And because curl is the operator that makes Green's theorem work, I like to call it Green's operator. I don't know, I find that satisfying somehow. I don't think it's a super common choice, but I like it. And then along those lines, I have in the past used this notation right here, GRN, just as a little abbreviation to suggest Green's operator. So I don't think you're going to see this GRN notation very many places, so probably the most likely place you are to see this is in my old midterm exams. Right? But anyway, when you do, all that means is curl, a.k.a. circulation density, a.k.a. that formula, a.k.a. the thing that makes the theorem work, all these different things. Okay, how are we doing? Everybody all right? Okay. All right, so let's talk again, let's talk a little bit about how to interpret curl in this context. And keep in mind, it is circulation density, right? So this thing, Green's operator, a.k.a. curl, our quantity that it's a density of is circulation. The extent to which the fluid is flowing along the curve as the curve kind of goes around in a loop, right? And the interpretation that we took last time then of circulation was circulation represents overall grand total how much the fluid is kind of going around the closed curve. So if you think about it then, curl, being a density of that quantity, says, okay, on little pieces of area, how much of the overall fluid rotation is happening within that little piece of area per unit area. And altogether, it kind of represents the extent to which, at a point, locally, how much the fluid is rotating at that point. And because it represents how much the fluid has kind of a rotational aspect to it, there's this notation, rot, R-O-T. And that's this notation. I was going to say the last one, but not quite the last one. So another notation that you will see sometimes, not super often, but sometimes. Okay. Is everybody okay so far? So the last one I just have to mention because it's in the book. I don't actually care for this notation much. In fact, I really don't care for this note. I think this is an unfortunate notation. The thing that makes this unfortunate is it expects that you take a vector field and compute del cross, but wait a second, cross. Now we acknowledge this is a notational convenience. This is symbolic nonsense, right? It's not literally a cross product of vectors, but you compute it as if it is, and to compute as if it is, we need f to be three-dimensional. That's how cross products work, three-dimensional. Check it out. Our vector field is not three-dimensional. That's bad. Right? This notation has a very serious shortcoming because it suggests something that really doesn't, square peg, round hole. It doesn't work. Right? So I've always been uncomfortable with this notation. Now that said, there is a scenario that you can generate to describe what's going on here, relate it to a more sophisticated theorem called Stokes's curl theorem, and view Green's theorem as kind of a special case in a way, but there's a lot of setup that has to be done. It has to be done just so, and I don't think it's worth the setup time to make that connection. So I will say there is a point of view by which you can kind of motivate this notation. It's a long way to go for, wait a minute, what was the advantage again? What do we get out of this? How does this notation help us? I don't see why this notation is any. How about we just call it curl? It's just so much easier. It's doesn't demand a setup to make sense out of it. So I don't care for this note. I'm going to go ahead and cross that out. It's not wrong. It's just it asks a lot of the viewer. Okay. All right. So, new integral theorem, new density theorem, new accumulation theorem, I might say. Okay, all right, let's do one. Here we go. We want to compute, it says here, we want to compute a vector line integral. The curve is given, the oriented curve is given. The vector field is given. And how do you compute? And look, you could do this the old-fashioned way, right? Up to now, how do you compute vector line integrals? You parameterize the curve. You plug and chug, pull back through the parameterization, follow all the rules, and then you work out a resulting integral. And let's just kind of try to anticipate how is this integral going to look. When you parameterize the circle, trig. X and y are like cosine and sine. X and y in this formula for the vector field being cosine and sine is going to make for some weird stuff, right? We're going to have tangent of a trig function. That's weird. I don't remember how to integrate stuff like that. Is that a thing? Do we have any pat rules for how to integrate stuff like that? It's a problem, right? So I think if we were to crank this out the old-fashioned way, I think it would be inconvenient and, at best. That's if it's possible. So this is a hard problem if we were to just brute force it. Everybody see why this looks pretty nasty? All right, so let's think about another way around this. Well, we do have right here a brand new theorem. The brand new theorem says that if you want to compute a vector line integral, you can just compute a double integral instead. That sounds nice. Maybe this is worth a shot. Maybe this will help us. But wait a second. There is a catch. We have a line integral to compute, sure. But does Green's theorem allow us to compute any vector line integral? Very much no. There is a very important catch on this, and it says so right here. This is only for circulations, specifically boundary circulations, not just any old vector line integral. Very important little thing. If you try to apply Green's theorem to a vector line integral that is not around a boundary, you will get nonsensical answers. It doesn't make any sense at all. In fact, if you look at, again, how did we develop this, the only reason that this worked out in the first place is because we were looking at boundaries, and we have these overlapping edges that always cancel because they're boundaries. Right? So this only works for boundaries. And so before we start writing stuff down and plugging and chugging, we better double check and make sure that our curve here is a boundary. And I'm sorry to report, it is not. All right, so there's what C is, clockwise going around the unit circle. Is the region on my left? No, it is not. So we cannot apply Green's theorem here. Does everybody see the problem? Okay. Please be very, very careful about this. I can't emphasize enough how important this is and how your bridge is going to fall down if you're not careful about this. So this is a very important aspect of problem solving. So let's see here. The little trick that allows us to work our way around this is very clever. And it goes like this. If I am interested in that oriented curve clockwise around the unit circle, notice that has a lot in common with this curve that goes counterclockwise around, which, by the way, is a boundary. Right? There's a really strong connection between this blue curve and this green curve. They're traveling over the exact same curve. It's the same underlying curve, just opposite orientations, right? And when you have an opposite orientation, remember we had this theorem from a couple days ago, whenever that was, that, opposite orientation? Yeah, cool, no sweat. Compute the other way, compute the easy way, and then just don't forget you have to compensate with a minus sign, right? So that's what we're going to do here. We're going to recognize we've been asked to compute a non-boundary vector line integral. And, well, that's only one minus sign off of a vector line integral that is, in fact, a boundary vector line integral, a boundary circulation. So at the cost of that one little minus sign, we can take a dead end. This isn't a boundary. We can't apply Green's theorem at all. And, again, you got to keep your minus sign. Don't forget that minus sign. And we've turned the question now, bulk of the question, into just computing what is now a boundary circulation. And boundary circulations are what Green's theorem does. Right? Green's theorem computes boundary circulations with a double integral of curl. Right? And that's just straight up applying right here. If you have a boundary circulation, it's a double integral of curl. Okay, and it's basically all over with the shouting. At this point, by the way, of course, don't forget to carry over your minus signs. Right? Real easy to accidentally forget that. And it's come down at this point to just, I've got to compute the curl here. And how do I compute the curl? Well, we have a formula for curl. Here it is. curl, aka Green's operator, aka circulation density, aka various other. There it is, dq dx minus dp dy. Again, some details to be worked out, but that's your formula you can use. Yeah.
Just to clarify, this curl, it's not related to like the del cross F curl, right?
It's related. It has a lot in common. Your question actually is why, for the longest time, I didn't really like to call it curl, because it's not quite the same thing, but it is actually closely related.
Okay.
Yeah, but the one that we saw in Chapter 3 was a three-dimensional curl, and this is kind of a two-dimensional analog of that three-dimensional thing. And it's a scalar instead of a vector, and yeah, it's different in some significant ways, but plays analogous roles. Yeah. So anyway, formula, dq dx minus dp dy, pretty easy to compute here because there's my q, its x partial is 3. There's my p, its y partial is 1. So dq dx minus dp dy is just 2. And that turns this into a super easy integral, which is pretty easy to evaluate as minus 2 pi. And we win. Didn't have to parameterize anything. Everybody see how that works? It's a really cool trick. Saved ourselves what might, I mean, I don't know, but it does not seem like it'd be a very promising integral to have to compute. If you were to try to do this by plug and chug, pull back through the parameterization, I think it's going to be a bummer. Okay, yeah.
Does this have anything to do with the fact that it's the perimeter of our unit circle and we're going in the opposite direction, so of course it'd be 2 pi? Or?
That's just kind of a coincidence. Yeah, the fact that the 2 pi is the perimeter, yeah, it's a coincidence. Okay. I mean, if I had made this a 7 instead of a 3, then it would be 6 pi.
Oh, yeah.
So yeah,
so
it's a coincidence. Yeah, totally. Yeah. Right. Okay. All right. So. Be careful about the orientation. By the way, as in a couple of instances in this course, even though the orientation just amounts to a minus sign, right? Don't make the mistake of thinking, oh, well, it's just a matter of a sign error, and sign errors are not important. This is not just a sign error. That minus sign, aka that minus sign, is how we manifest the very important issue of orientation, which is a sophisticated idea of Math219, and boundaries, which is a sophisticated idea of Math219, right? That's a big deal. So the minus sign, getting the orientation correct, treating the orientation correctly, even though it only comes down to a minus sign, again, a large part of the problem, probably 4 or 5 points on a 20-point question, is correctly interpreting and handling orientations. So please do take that seriously, and don't underestimate the importance there. Okay, last thing here. This last example is actually quicker than it might look. We've got this curve that is like so. And it's got 4 pieces to it, and I guess we could parameterize each of the 4 pieces. That's going to be kind of tedious. Let's not. And let's figure out how we can use Green's theorem on this. The bummer is that this curve is not a boundary. Because at that point, while we are moving with the region on our left, at this point, you'll notice going in the direction that it says to go, the region is not on our left. So this is not a boundary curve. But here's the clever move. Real clever move to take this curve, break it up into a bit more pieces. It's those 3 pieces plus these 3 pieces. Now, there's a good news, bad news deal here. These 3 pieces here are literally the boundary of D1. Sweet. Right? So we've written sort of half of our curve as being literally a boundary. We love boundaries because then we can use Green's theorem, and that's going to be totally awesome. This blue stuff over here, not a boundary. But it's exactly wrong. Right? It's everything about this is the exact negative of boundary of D2. It's the exact curve that is boundary of D2. It's just not going the correct direction. So again, we're only off by a minus sign. So those blue are the opposite orientation of a boundary. Right now, I had to kind of split things up around to make this work, right? If I were to look at the original curve that we were given, the original curve is not a boundary, and the original curve is also not the negative of a boundary. It's just not. But if you cut it in half like this, then everything works out nicely. And so likewise, we get the green integral, which is a boundary. Minus sign to recognize that we're oriented backwards, and then we're looking then at another boundary line integral. Boundary being literally the boundary of D2. Okay. And Green's theorem, plug in some numbers, everything works out pretty great at this point. There's Green's theorem. There's Green's theorem applied to these two different regions. You got to compute the curl of this vector field. The curl of that vector field ends up being a constant. It's just 9. Make sure you can do that. dq dx minus dp dy ends up being exactly 9. And so we have this. And all we have to do is compute the area of D1 and the area of D2. That turns out those areas are the same. And our answer is 0. So it works out really nicely, yeah.
So can you say that this is like a symmetry argument?
No, it's absolutely not a symmetry argument. No, it's really very importantly different from that. It's just work. It's the orientation. I mean, there is a cancellation, but it's not because of symmetry. It's because of orientations and there's a lot of other moving parts here.
Okay.
Yeah. Okay, all right. See y'all later. Have a good rest of your... Oh, wait. No, have a good weekend. Yeah, cool. See y'all. Don't forget about attendance.